Alright, are we live? Hello, 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 hello. Plan unfurls. Do I trust my heart or just my mind? Why is truth so hard to find in this world? Yeah, in this world. 'Cause I am due for a miracle. Alright, singing the right songs. So, I want to keep listening to this music. Yeah, the song I'm listening to. Till I understand or go blind. All right. What I want to do. Yeah, you can't hear it because I have it muted, but it's great. It sounds so good. Um, what I want to do is. I'm still listening to the song. I'm sorry. It's really good. Um, take a look at this problem. So basically, it's actually really distracting. I can't focus at all. What I wanted to do was just try another problem because I was working on a problem for a while, and and I basically found another solution, which is great. I should come back to it, but I was kind of getting this like uncomfortable feeling like I'm spending a lot of time on that problem, and like there are other things I probably should be doing with my time. Excuse me. In addition, like beyond just solving these problems. So I always have this tension of like I feel like I should be solving problems like to practice, but also like basically attending to my personal life, put it that way. And yeah, lately I've kind of had this like tension where it's like some of these things kind of have like like expiration dates, sort of, and I'm like kind of afraid to contend with these things. I think technically I could get, I don't know, like some of the things I could either technically get a fine or even break the law if I don't um, do them at the right time. So I don't know. I'm not really sure. Yeah, I don't know. But the longer I wait, the worse it gets for some of those things. Um, they're like, I don't want to get into too much detail, but we'll just say I probably should do those sooner rather than later. Yet here I am solving the problems on the internet. And like, I don't know, part of me was like, well, I should be solving problems, but also one of the other problems I was working on was going to possibly take me a very long time. So my thinking is like I'm kind of conflicted about it. I'm thinking like, all right, maybe I'll just take a break from that, come back to that whenever. Probably should just go take care of those other things first. Probably shouldn't even be solving problems at all. However, I don't want to let too many days go past without working on something. And I had kind of taken something of a break because I don't know, I had kind of a, let's say, wrestling with my faith, something like that. Something happened and it was pretty difficult, I guess, emotionally, something like that. Um, More than just emotionally, but it was just difficult, and I kind of had to sit and think about it for really a few hours. And praise God, just thank God, praise God. He's there to comfort me through my struggles and my thoughts, and I'm really grateful, extremely grateful, glad to be a Christian. I had actually recorded a video about just thoughts on God, just because it kind of got me going, and I don't know if I want to release that though because I don't know what value it would be. I was kind of just rambling about how I felt about God, um, and particularly in that moment, that what I was kind of contending with, and excuse me. So what was I trying to say? I don't know. There's like a million things for me to think about, and it's like it's kind of overwhelming. It's too many things to do and think about, and I don't know, man. It's hard. It's hard. It's really hard. It's really hard. It's really hard. But again, praise God. I have God, and that's all you need. That's it. It's fine. Don't worry about it. Don't worry about it. I mean, not that things aren't important and you shouldn't worry about them, but like, even if everything falls apart, you make all the worst decisions, and get thrown into prison. I don't think I'll get thrown into prison, but even in that place where I think Paul actually wrote a lot of his letters from prison, so it's not, as long as you're doing right by God. Now, granted, being negligent is not it's not a godly thing to do. Not trying to justify negligence here, but I don't know if I don't know. There's a part of me that's like struggling with that actually. That's just among the things I'm kind of contending with is like, am I actually being negligent or am I being, um, yeah, probably just being negligent. probably just doing the wrong thing. Probably should take care of those things I need to take care of. Well, my thinking is like, well, if you don't have the ability to take care of certain things and within certain timelines, then what are you supposed to do, right? Like, if you can't help it, right? Something like that. Yeah. I'm probably just in the wrong. Anyway, let me look at this problem. We'll solve a few problems, get my mind off of those things, and I'll try to take care of the things I need to take care of. Probably be fine, but it's definitely kind of a little bit nerve-wracking. So what's interesting here is the constraints. So I want to say this is probably a problem where we don't need to have a particularly efficient algorithm. Given a non-empty array nums containing only positive integers, find if the array can be partitioned into two subsets such that the sum of the elements in both subsets is equal. Oh, well, only two subsets is actually pretty easy, believe it or not. There are only a linear number of possible. Oh, no. No, I'd actually take that back. No, actually, it's not as easy as I might think. It's actually maybe not. So basically, you could rephrase this as if you added all the numbers together and divided by 2. First off, that has to be even, and second, so actually this one immediately would be false, right? Because you could do 8, 10, 11. 11 is not divisible by 2. So you can kind of have an efficient check there, but beyond that, there are an exponential number, 2 raised to the n, where n is the size of the set. There's an exponential number of possible subsets. And basically what you would do is one approach would be loop through all of the possible subsets, calculate their sum, and check if their sum is equal to half of the total. Right? That's all you'd really need to do. Now, what I think ultimately I'll end up doing here is loop through the subsets, however, use a brute force approach that terminates early, basically pruning the branches of the tree. So brute force approach that terminates early, and the reason this would be efficient enough is because you terminate. Basically, the terminating early would be that if you go over half of the sum, then you can't add any more values, and so that anything beyond that branch of possibilities immediately falls off. And yeah, just thinking if there's a different way to do this though. That might be good enough. That's probably good enough. Also, the numbers being bounded by 100, I think is interesting too. I think you could probably make something using that as a parameter. In other words, like base an algorithm off of that constraint, and I think you'll have like an extremely efficient algorithm after that if you do it that way. Just thinking. Yeah, I think so. Well, maybe. I want to say you can use a dynamic programming solution because these numbers are small. I want to say something like that. I don't actually know because you're dealing with sums. And so, am I back? Sorry about that. I think my connection, something happened with the connection. Looks like we're back though. So I'm thinking maybe of a dynamic programming solution though, where you could do something in quadratic time, and what you would do is you have basically 200 times 100, right? Yeah, I think you do it that way. I think you use quadratic. Yeah, I think you use a quadratic programming approach. 200 by 100 is only 20,000. You can have so that all the numbers that you're going to be dealing, all of the sums are going to be within that range, between 1 and 200,000. And so what you can do is basically loop for each value. I guess you'd have to kind of start initially at 0. So it would be 0 to 200,000, right? Including 200,000, 200,001. And you can add any of the numbers to that value to get sort of the next set of possible values. And then for each of those numbers, you can get the next set again. And basically, you kind of would just set the value that index to true or not, like whether or not you can actually reach that particular number. And yeah, I guess what you would do is you would just go one by one from 0 to 200,000, and you check if it's true, right? So if starting 0 is true, then you add all the numbers to that and set those values to true, and then go to the next one and say 1. Do you have a 1 there? If that's true, then add the numbers again. So you can do a quadratic programming a solution. I think it's pretty efficient. Utilizing the bounds of this here. Yeah, I would do it that way. How much time we spent on this? 12 minutes thinking about it. Not too bad. Pretty quick. Relatively quick. All right, so we're going to use booleans and vector booleans. You could technically use a bit set for this too, but we're not going to. And we're going to say just vals or check. I don't know. Bits or possible, we'll say. And we're going to say it's all going to be true, and it's going to be nums.size times 100 plus 1. And that's going to be true for all of those. I believe the number comes first and the value comes second. And now we're going to say for, so we can do, for outer for loop. So we're going to say int I equals 0. I is less than possible dot size plus I. You actually don't need to go that far. Well, okay, yeah, I guess it's, yeah, all right. You don't need to go that far. We can do, we're going to use int total is standard accumulate of nums.begin, nums.end, 0. And we're actually going to go to if terminate early, total modulo 2 equals 1, or it's not equal to 0, immediately false. Otherwise, let's say total divide equals 2, or bit shift to the right 1, right? And then we're going to say less than or equal to total. And we're going to say if possible, and actually should be false. That was my mistake. Possible of 0 should be true. Okay. So if we're possible, then we're gonna loop over, just do const auto x nums possible of I plus x equals true. Right, it's gonna be idempotent. So if it's already set to true, it'll just be set to true again. And then we say if return possible of total. Yeah, something like that. Is that it? That's all I gotta do? I think that's it. Yeah, I think it's, how do we do? It's 16 minutes, not too bad. Let's see if we can come up with some, I don't know, let's just get some random input. Oh, it's gotta be less than 100, right? Oh, none of these are less than 100, huh? I don't know, just a bunch of random stuff. See how we do. All right. I don't know. Let's go for it. Who knows? Oh, that's upsetting. Wait, what? I probably should have tested more test cases. Definitely should have tested more test cases. 3, 5, 8. Okay. True, false. What? 8 divided by 2 is 4. Oh! I know it's wrong. That's my mistake. Yeah, I am wrong. Oops. No, that wasn't a test case thing. That was just kind of being a little too. I actually was being a little overconfident. Yeah. Wrong. 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 The reason this is wrong is because you need to know which numbers you've already used to get to that point. Oh. Okay. Yeah. Because you're supposed to not add those again, right? Because we added 2 twice. That's a mistake. These are subsets, not. These are subsets, not. Not. I guess selections with replacement, if that makes sense. Oh, that was a big mistake. That was actually. Yeah, that was a big mistake. Alternatively, what we can do is at each position we can store the numbers used to get there. And yeah, I mean, I'm just thinking, oh, this is not good. I am very wrong. I'm very wrong here. Okay, sure. Uh-oh. Uh-oh. Oh no. Let's think. Hmm. Huh. Uh-oh. Uh-oh. Now we could still do the solution I was describing before with the depth first search, which where we terminate early, or we with pruned leaves. Can still perform a depth first search with the pruned leaves, but that's so unsatisfying. And I was so confident in this too. It's almost, that's embarrassing. I'm embarrassed. I was so confident. Ouch. The problem with trying to not add, like, actually we could do it this way. Yeah, we can. We can still do it this way. Yeah. Okay. Let me think here. Yeah. All right. All right. We could save this. We could salvage this. It's not. It's just. Okay. It's a little tricky, but we can salvage this. We can actually keep track of the sets that give you true, and so instead of true, it's going to be actually a vector of unordered sets. So I wasn't too far off, but I think we could do it this way. I want to say we could do it this way, although that's yet to be seen. So still do a similar thing. However, it's going to be an empty set. Let's just constant expression. Call it n or x or t or something. I don't know. I just want this to fit on one line. P size. Do it that way. Yeah, I just want this to be like kind of moving off down here. Okay. So yeah. So this is going to be. We're going to do it a little bit differently here. So it won't matter because the number of values in each set and the number of sets. Actually, this might matter. I don't know. I don't know what this is going to look like. This is kind of. I don't know about this one. Yeah. Okay. Let's do it. Let's do it like this. So, I don't know. Well, we'll see. Let's see how this goes. So, possible 0, we don't need to touch. Actually, indeed, we only need to go. Well, yeah. All right. All right. We'll do possible 0. So, if it's not empty, let's say if I equals 0 or not possible I dot empty. So if you're empty, then you're gonna get skipped, right? So if it's not empty or we're at the first instance, what we're going to do is we're going to look at each number, right? And we're going to say if I is not in possible I, if possible of I dot contains, or count really, of I or next, I did that wrong. Hold on. We're gonna say for const auto, or just auto set in not nums, but possible of I, right? So for each of these sets, whoa, what's going on? Okay. Okay. Maybe I should explain it in English first, but it's fine. So for each set that we're looking at that spot, possible of I, actually there could be a lot of these sets, by the way, so this may not be the best approach. What we're going to do is, for each of those sets, if, and it's not going to be x of nums, it's actually going to be, you actually need to do it this way. It's going to be the indices, so index, index is less than nums.size. We're going to be storing the indices rather than the numbers themselves. For each index, and then for each set, if this index, if this set dot contains, or dot count, excuse me, this index, if that's 0, we'll say not, right? So you don't contain that index, then you're going to say possible of I plus x nums of index, say int x. Okay, so you have x. You're gonna add, you're gonna say this dot. So actually it's a set of sets. See, that's the problem. A set is not enough. It's gotta be a set of sets, which is an issue. This is actually not gonna work as well as I'd like it to. No, this is not going to go how I thought it would. Set of sets. Uh-oh. I think I could just declare the size, right? Don't think I need to say more than that. Yeah. So as long as we have some set, then we're going to loop through, basically for each number, loop through each set and say if this number is not in that set, you're going to add to the set of sets ahead that set with this value inserted. I'll do it this way. Just call it temp, and we're going to say s temp.insert. So it's actually a copy. So this is not a good idea, what I'm doing here, quite frankly. This also could be const auto. And this is not really a good idea, I think. I don't think this is going to work. And then insert temp. Okay. The reason why I think this is not a good idea is because of how many possible sets there could be. There could be a lot. Oh, it's not a const expression. That's my mistake. Yeah, because that's not a const expression either. What is going on? Can I not have an unordered set of unordered sets? Is that the problem? That might be the problem. Yeah, I think that's the problem. We can do a set of sets, it's fine. Doesn't necessarily need to be unordered. Or you do a set of unordered sets, which is interesting. Could be either way. Yeah, let's try that. What does that look like? Still having issues. What if we did a set of sets? What does that look like? Is that not the problem? No. Yeah, that's what it was. The set of unordered sets, because you can't. You have to write your own hash function. I could update that, but we'll leave that as it is for now. It's not really that much of a penalty to put this into have logarithmic access times, insertion times rather than constant. Shouldn't be that big of a deal. So the problem is that even though this will probably work, the issue you're going to run into is the largest. So what could happen is the number of sets you're dealing with could be very large. Specifically with 200 numbers, you could have 200 choose 100 different sets, which is a lot. Well, yeah. I don't actually know in practice how many different possible sets you end up with. Let's see. This might time out if we use a large enough number. Like, let's try it. Let's just try it. See what happens. We don't need to go crazy. You can actually do a scripting thing. I want to do that. I want to try that. Well, I'm already halfway there. I mean, not halfway, but already pretty far. What you can do is write a script to generate these numbers. And just thinking, how would I do that? I could do like print. Oh, actually, we don't need that many, do we? I don't know what the running time for this algorithm is. I think it's inefficient. 0 milliseconds, really? You're kidding. Is that because it's odd? Oh, whoa. Whoa. Oh, no kidding. I wasn't expecting that. All right. 1 to 51. 1 to 51 would be 51 times 52 over 2. Yeah, it was 1. It's 26. It's 13. Oh. 1326, so we said. Okay. Interesting. And for some reason, you actually don't need to move to total. And this is also probably why it's wrong. It's index at that point. I don't know. Wait. So this is still, yeah, I probably should use different terms for index. Maybe like I and J would have been better, so it's not so confusing. Yeah, I think I made a mistake there. You would say, you can do J. Let's do J instead of index. Let's do J. That's better. It's really confusing using indices that are kind of too similar to each other. You insert J, and it's possible of I. Insert temp. Now we got false, but expected true. Why did that happen? Or if possible of I is not empty. Go through J for each number, for each set, and the list of things that are possible to that point. If J is not found in that set, create a set out of S, insert J into that set, insert that set into I plus X. No, it's actually not I plus X. Oh, it is I plus X, yeah. Yeah. Okay. What's the issue exactly? Why is it? Yeah, it doesn't need to be equal. That doesn't really. How come we're not getting true for this? Why wouldn't this get true? Why don't we print each possibility, right? You know what we could do? Actually, this is not the this. I don't think was supposed to be the problem I was expecting. I was expecting us. Oh, that's why. No, that should be fine. The problem that I was expecting wasn't this. It was actually. By the way, this could be an unordered set of sets. I'm pretty sure this could be an unordered set of sets. No, can't. Okay, never mind. What am I missing here? Yeah, let's print. What I was expecting to go wrong here was actually that that it would be correct, but it would take too much time. Not that it would be very fast and be wrong. Wasn't expecting that. All right, so let's go through basically print the whole set of possibilities. So I is 0, I is less than or equal to total, plus I, and we're going to say for const auto ref s in possible of I, we're going to say for const auto x in s, we say print a new line. Oops, why is it? Oh, I was hitting X instead of copy. We want to print, well, really just I. And then, oh, actually it should really go there. We'll just have that and make that delimiter. And then we'll say, do something like this. That should be fine. And yeah. You can do, well, yeah, it's fine. Not a big deal. We actually don't want to put, we want to put them all in one line. Each set. And then, yeah, something like this. Something like this. Pretty like rudimentary, not really caring too much about the what do you call it? Not caring too much about the what do you call that? I actually don't know what the term is for that. Excuse me, the format, the neatness of the format of the output. In some cases, the output will look kind of funky. So, oh, looks like all the sets are empty. Okay. Okay. Oh, that's because the first set is empty. Oh, I see. Gotcha. That makes sense. Right. You know what we could do? We could just have an initial loop. Yeah, okay, I didn't really. Okay, makes sense. Also makes sense why it's so efficient. It's just 0 straight across, done. So we just say for const auto x in nums. It's actually not nums. It's I. It's actually call it j. Keep it somewhat consistent. Possible of j dot insert a new set. It only contains one element. Nums of j should be. Which contains one element, which is j. Something like this. Wait, what? Can we not do this? Excuse me? This doesn't compile? What do you mean this doesn't compile? Maybe I can't do what I want to do here. Oh, come on, really? What about this? That compiles. Why? How about that? That compiles. Apparently that compiles. Okay, that was the that was the problem I was thinking I was gonna run into before. It's like this is not efficient enough. While correct, definitely not efficient enough. It's kind of annoying that it took this long for me to figure out what was wrong. It took me a while, but we got there. We figured it out. We realized. All right. So, yeah. I mean, okay. So at least this is correct, though. I think, right? Yeah. All right. get rid of this debug. Yeah, that was what I was expecting. Obviously, ran into some issues here. But this is not efficient at all. It's actually really inefficient. I can explain why shortly. I think I want to say that I can make this more efficient, but also 46 minutes. One, I'm kind of disappointing myself for getting this wrong the first shot, thinking that it was that easy. So the other thing is, I think there's a way to make this more efficient, but gotta think about how it could be done. Excuse me. Knowing what numbers you had to use to get to a particular, that's basically what this does, is this keeps a track of all of the numbers you used to get to a particular spot, particular sum, and then from there, for each of those sets, you can decide, well, if this number is not in any of those sets, or if there's at least one set that's not included there, then you can add that number, add it to that set, and get to the next spot. It's just the problem seems to be maybe there's a better way of doing this. Like maybe you can just say, well, does there exist any subset that is equal to this particular number? And is any subset possible? Any selection of these numbers? That actually might be relatively easy to figure out. Maybe, I don't know. I want to say, like, you could subtract. Yeah, again, the problem becomes this dynamic programming thing, not dynamic programming thing, but this like kind of backtracking thing where once you use a particular index, you don't want that to be available again to try to use. Excuse me. I mean, an alternative question, really the same question, is given a particular value, can this subset be summed to that value? That's the answer. That's the question I'm trying to. Does there exist a subset that could sum to that value? And I want to say something like, well, you could select any of the numbers, and then you would have a recursive question, right? You have the same question, but now missing that particular number and reducing the total. So you can write a recursive solution where you remove that index from the vector for each of those sub-problems, sub-questions. The problem with that, though, is I think, like I said, there's so many possible subsets that really gets pretty dicey. That's basically the dynamic solution that we just wrote. That's kind of what we just did. We said call this function again, but add one of these, pick one of these indices to add, and remove it from the possibilities. Or really add it to the things you've already selected. The problem though is that one number could have a ton of different ways to get there. That's a tricky question, huh? You can't just try every possibility. That's way too inefficient. You need to do some kind of pruning. Interesting question, man. Interesting question. Excuse me. Yeah, I gotta really ponder this for a while. I gotta ponder this for some time. Let me... Oh, my back. Oh. I'll be right back. Never mind, not going anywhere. I was gonna just start writing down on my notepad. Just start drawing things, but actually I could do it for right here. Ooh, excuse me. Now the question is, why, what, smiley face. The question is, I don't know, I don't have a solution. I don't have a solution, I don't. Oof. I don't want to do the backtracking, that seems bad. Yeah, it doesn't seem good. Ooh, excuse me. I kind of want to use like a sliding window doesn't really work either, because like if you sort all the numbers and then you want to add numbers to get to the total that you're looking for. The problem with that, I think, is yeah, the problem with that is that I think I want to say like the subset has to be equal to the number, and like you could have holes in your sum, something like that, if that makes sense. I don't know, I'm trying to think of an example where like you might do like 1, 3, and 5, and there could be a 2 and a 4 in between, and this gives you 9, right? So you're trying to get 9, But if you did 10, 20, 40, 30, 50 maybe, and this is 90, and maybe this is 31, and this is 91. Right, you wouldn't have 50 and 40, and you need to have the 31, and you would then skip the 20, or you could do, this could be 91 also, but something like that. This is probably a better example. Well, let's do 35 here, right? So you would skip the 35 and the 20, and you would go 10, right, if these were sort of in between. How would you do in this example? How would I do in this example? Yeah, I mean, my thinking was like, you have an array of, can you get to this particular value? The problem though is, from that value, what numbers are left to get to the next spot? And it kind of depends on what path you took to get there. Because whatever path you took to get there, it matters how you got there, because once you can't use those same numbers again to go to the next spot. And in that next spot, you similarly you can't use those same numbers again, even again. And actually, what this ends up kind of being like is, like, from a recursive perspective or something like that, it's sort of like if you had 200 Boolean true or false parameters, right? And the issue there is that that's 2 raised to the 200th different possibilities, right? Like that's kind of that's the number of possible sets you could have, subsets, excuse me, of 200 numbers is a lot, 2 raised to the 200. So that's not really possible, not really a possible way to do this. Yeah, it's a lot. That's a lot of possible ways. That's basically if you wanted to keep track of all the paths possible ways to get to a particular number. That's just to figure out which numbers you can't use to get to the next spot. Excuse me. Yikes. Stuck on this problem. Uh-oh. Uh-oh. Thought I was so clever too. I was thinking I was so clever too. I really don't want to do the backtracking question, backtracking approach. I don't think it's the right way to go. It's pretty inefficient. Really want to try to find something that's polynomial time. Although maybe that's too much to ask for. Maybe this should be done by using backtracking. And there's just no really just spinning my wheels trying to find something better than that. I don't know, man. The constraint that the numbers between 1 and 100 really is kind of messing with me, because I feel like there's got to be a way to do this more efficiently using that particular fact. I didn't realize this wasn't charging. I don't know, man. I'm kind of stuck. Gotta think about it. Gotta think about it some more. Don't truly know. I don't know. It actually doesn't. I was gonna say, because there's duplicates, it kind of makes things complicated, but it actually doesn't make it complicated if there's duplicates. Yeah, duplicates isn't really a problem, because there could be, like I said, there could be multiple different ways to get from one point to another. Or rather, the multiple ways that you could have gotten to a particular point. Yeah, but the issue is, like, what paths do you still have once you're at that spot? What particular options do you have? And that kind of depends on how you got there. Now the question is, does it really matter that much? Yeah, it kind of does. Kind of does, because if you got there like way A and then you got there way B, and there's some elements that are not in A and some elements that are not in B, And for the path for B, you could use those elements, the ones that are not in B. And for path A, you can use the elements that are not in A. But the problem is the elements that are, like when you get to the next spot, right, whatever element you add, that for, so let's say A prime and B prime, right, those different elements, like let's say you just picked one element that's in A and one element that's in B, is not in, one element that's not in A and one element that's not in B, like an X and Y, and you have A prime, which is A included with X, and B prime, which is Y included with B. You get these two different paths now to this spot, and you have the same sort of consideration where now if you want to pick the next element, it's got to be an element that's not in B prime and or an element that's not in A prime. You can't pick elements that are in both. So the intersection, I guess, you can't pick those elements. Yeah, you won't be able to pick the elements that are in. The question though becomes like the elements that are not in the intersection are possibilities, but how do you even calculate that intersection? I think is the question, right? Like, how do you know that you used a particular element for all possible paths? If you're not even keeping track of well, yeah, see the tricky thing there is, actually I don't know if it matters. I don't know. Now I'm thinking about it. I don't actually know. Oops. Well, actually, like keeping track of the total intersection of things to a particular point where you can't use, definitely can't use certain elements. I think you run into issues with that too, because you kind of need to keep track of all the paths that got there, and I guess you would build the intersection as you go. Well, okay, yeah, I guess that works. I guess technically that makes sense. Yeah, that's interesting. Okay, let's try that. I don't know. Now I'm like, my noggin's a jogging here. I don't know. Now I'm really uncertain. All right, let's try that. Let's do something like that. So initially we have this new set. We're gonna do a set of sets. Actually, we're just gonna do not a set of sets. We're gonna go back to what we had before. If this works, it'll be very efficient, but part of me feels like this shouldn't work. Okay. Okay. Then what we can do is for each index, its value x, we say S is possible of I. So actually what we want to do is I just want to see that there's an operator set operators. Hold on a second. Oh, tie. Interesting. I think tie returns a tuple, right? Yeah. It creates a tuple. You use tie or make tuple. They're very similar to each other. Is this not oh, use forwarding. Oh, that's interesting. Deducing the target type from the type of arguments. Oh, interesting. Decay. Application of decay results in reference wrapper. Oh. Oh, that's interesting. Unwrap decay. I don't know what decay does. Make tuple is a little bit different than tie. Forward is tuple. Tuple cat. Cat any number of tuples. Oh. Whoa. Calls a function with a tuple of arguments. Whoa. Whoa. These are things I don't really use very much or haven't looked at. Excuse me. We should look at what decay means. All elements. Tuple object composed of all elements of all argument tuples constructed from standard get j forward ti arg for each individual element. Tuple printer. Oh boy. What is going on here? Uh-oh. Template metaprogramming. Foobar, tie, double cap, make double. Oh, that is just confusing. T1 foobar T1 tie N 7 T1 10 test 3.14. What does tie N do? Oh, well, that's interesting. I think that creates a reference, huh? That's confusing. Tie is an L value reference. Oh, tuple of L value references. Oh, that's wild. Whoa, that's a trip. Oh, I understand now. Okay, that is so confusing. Yep. So you can actually, wow. You can unpack a pair. Whoa. Standard ignore. Nice. Oh wow. So you can unpack using tie because these are L values. Structured binding. So tie, oh wow. So tie is from C++ 11. Oh wow. Okay. Interesting. Object of unspecified types to any value can be assigned to with no effect intended for use of standard tie when unpacking a tuple. Placeholder for the arguments that are not used. Wow. So structured binding is C++ 17. But the thing is, you can use structured binding with tie. Oh, okay. I see. I get it now. Yeah, I should make use of that. I kind of wondered that. Something like that. Binding an array. Yeah, structured binding. Pretty interesting. Whoa. I realize I'm kind of getting off now. So all this has very little to do with the problem we were looking at, but I just kind of was curious about structure binding in C++. Felt like I didn't know all of the things I probably should know about it. Alright, anyway, so yeah, apply. This is really interesting. Apply. This is definitely, wow. Wow. Generic T first, T second, first, second. Add int. Whoa. Whoa. Apply, add, standard pair, 1, 2. Oh, okay, interesting. So you'll call this function with a unpacked pair. Could be a pair or a tuple. Can't deduce the function type. Add generic, make pair. Oh, I see. So if you make the pair generically, it won't work. Couldn't deduce the function type. But here, add lambda pair auto. Somehow it works. Somehow that works. That's bizarre. Advanced example, my tuple. See out my tuple. Whoa. I don't know about that. This is kind of interesting. Can't make the pair here. Huh. Interesting. I guess the specialization needs to be generated first. Something like that. I don't really know. I don't know. I'm kind of surprised that doesn't work, but yeah, that's interesting. So call the function using a tuple. All right, that makes sense, I guess. It's a function and a tuple. Callable object, tuple arguments. Need not be a tuple. Anything that supports get. Standard array, standard pair may be used. Oh, that's really interesting. Oh, call a function with an array. Neat. Neat. It's kind of nifty. Anyway, what I was looking for was these operators for sets. Yeah, these operators overloaded for sets. Val arrays, bit sets, binary, val arrays. We don't have anything about we don't have anything about do we? I mean, does that exist? The intersection. Like it doesn't. I'm not really looking for the algorithm that does that, but the set itself. Also, this is interesting. This is like this gets into C++ 20 stuff. Already in 2021 over here. Just crazy to me. Crazy. It's crazy. Const auto. Look at these things. Set. Can we don't I see merge. Like if you want to find the intersection and the union for these sets. Sure. What would you do without using that? Um, so they do use these algorithms, huh? Or at least these folks do. That's from a year ago too. 8 years ago. Really, set intersection is. How old is set intersection? How old is this algorithms library, man? I feel like it's. I was actually still in school 8 years ago. Why does it feel like the algorithms library is like really old to me, or really new to me? I guess it's because it's new to my understanding. Like I didn't know about the algorithms library. How old is the algorithms library? Oh, no, didn't mean to click the ad. That was what I meant to do. Execution policies is 17, but yeah, most of this is from C++ 11. So most of this is actually relatively old. Still new to me, for whatever reason. It feels new to me, I don't know why. I guess it's just how I learned C++. Yeah, no kidding. Yeah, these are really old. Stuff is like C++ 11, a lot of it. Huh. Set operations. Yeah, these are like super old. Oh. Okay. Excuse me. Wow. All right. I don't really know much about uninitialized memory either. Uninitialized area of memory defined by range. I don't know how that works. Excuse me. Excuse me. Q sort, B search. Destroys a range of objects. That's really interesting. This is also really old. Probably concepts that are relatively new to me though, still. Working with the memory class, the memory portion of the STL. So how about how about set union, set difference? Yeah, I guess. Difference, intersection, union. I mean, this is what I want. Yeah, this is really old. This is from a long time ago, huh? It's execution policies. I don't know anything about that. A sorted range beginning at of elements that are found in both these sorted ranges. Don't know anything about execution policy. Um, back inserter. Can we use a set inserter? Interesting. Hmm. 3-1 fill. Can we do just an insert iterator or just a inserter? Yeah. Hmm. Basically, I guess we just create an inserter for the set. So, I don't know what to do. This is kind of, what do they call that? Somewhat unrelated, I guess. Yeah, let's just. Let's just say A, 1, 2, 3, B, 3, 4, 5, and then we have set result, standard intersection, set intersection of A dot begin, A dot end, B dot begin, B dot end, and then a standard inserter of result. What do we get here? Function template not viable. In 1, 2, 3, 4. What's wrong? No matching function call to inserter. So close all these. Oh. Test.end, huh? I don't, oh, okay. We'll try that. I don't actually know. Oh. All right. That worked. Sweet. Okay, so we know how to compute our intersection at each point. Okay, that's fine. Just kind of learning a little bit more about the STL here. So as you can see, I very rarely use. I kind of don't use very much from the STL. So the algorithm, to get back to what we were doing, where we, wow, we're like almost 2 hours here. Okay. All right. What I wanted to talk about, or want to think about, is I don't even remember now. Something about the STL. What's this saying? Right, so the elements that we can't choose from during our calculations, it's going to be the indices that we're not going to choose from for the elements. And the elements that we can't choose from really are only the intersection of the sets. And so you would take all of the elements that we weren't allowed to use before, as well as the new element, and you're going to take that intersection with what's already there, I guess, if that makes sense. And that'll maintain the intersection of all of the things that were used to get to that point, sort of as you progress. Now, the question that I have is like, okay, I could probably code that, but does that make sense? And is that actually what we need to do? Like, is that legitimate? Like, I don't know, let's say there's a lot of different ways you can get to a particular point. We want the intersection of all of them so we know what we can't select to possibly get to other spots. And then if we take another look, if we look further down at a node and look at all the paths coming in, yeah, we would want to know for each of those what the new value was that we used to get here, and all of the things that were used to get to this point. And you would take that intersection with, see, that's a tricky thing. Well, if there's nothing there already, then that would be the first set, right? And then all the other ones that come in, you take the intersection with all the other ones as well. Because the thing I'm afraid of is like somewhere down the line there's some overlap that occurs where an element, like there was a set of intersections on one point and a set of intersections on another point, and there was an element that these two paths both ended up using. No, it doesn't matter. I don't know if it matters. I don't know. It's hard for me to like prove that this works. Well, I think by induction it's okay. As long as you don't use any element that's in that intersection, then at least one path allows you to get to the spot you're at now. And I think the problem is that that path that allowed you to get there could have other elements involved that are gone because we're only considering the interest. Yeah, so I don't think this is correct. Yeah, I don't think it's correct. No, it doesn't make sense. Because yeah, you lose information once you take those intersections. Excuse me. You don't necessarily know which path anymore got you that spot, and then if that path is like the only path to get to another spot, then actually all of the possible values well no all of the paths can get you to the spot you're getting to next. If you're not using any of the values of the intersection, then every one of those paths to get there will get you to that spot too. Yes. Yes. Yeah. Because every path got you to where you're at, and then there may be some paths that use an element that you just used that won't go to the next spot. Because the element that you just used is actually present in one of those. But that doesn't matter. We don't care about those, right? Only care about the ones that will actually get you there. Which technically would be every path that, not every single path, but any particular path. Yeah, any path that gets you down there doesn't include that element, right? You can assume that. It's actually, I don't think you lose any information then. So I'm trying to think of how this could break. If we're somehow missing information, we get further down and these elements don't excuse me. Oh boy. Oh man. Just check to see if anybody's chatting. I don't know, man. I'm struggling with this. Maybe I should use an example. Well, I mean, I could try it on an example. You know, I could just use a simple example. Also, did I saved it? Okay, good. I want to say, man, I don't know. Just thinking. That would be extremely efficient if this worked, but the problem, I don't think it's correct. I think it might be correct in some cases, but I mean, it's a 50-50 chance for a lot of cases, right? Because this is just a true or false. But the problem is, yeah, just taking intersections like that, I don't think that is correct. There would be some path that we can get down there. Right, if there's only one path that gets us down there, and no, all the paths that don't have that intersection. Well, yeah, it could just be one path, right? It could only be one path that gets us down there. Well, any path that got to that point will get us down there as long as that particular element is not present. So if you look at the intersection, there might only be one path that doesn't contain that element. So that's the one path. Now in that case, all the elements in that one path can't be considered from that point on. However, you might have another, but you wouldn't know all of those you don't know what all of those values are. Yeah, that's the issue. That breaks it. That causes the problem. That was why I was saying, well, just use every path, every possible. Just keep track of everything, which is correct, but it's extremely inefficient. Yeah. Yeah. Trying to keep track of everything that was used up to that point. Yeah, if we only keep track of the intersections, that's not enough information. Because there could be one path that used a bunch of stuff that all the other stuff didn't use, and that's the only one that can make it, because that's the only one that you would reuse that element for. And so the other stuff that wasn't used for all the paths that descend from there, all the things that descend from there, should actually include the whole thing, not just the intersection of things. Should include all that other stuff, and it won't. I actually get the wrong answer. Half the time. Roughly half the time. Or, yeah. In some cases, I get the wrong answer. In those cases, half the time I get the wrong answer, I guess. Or, yeah, well, just say in those cases I get the wrong answer. You'll potentially get the wrong answer. So, okay, I guess. Find if the array can be partitioned into two subsets. Let's read the question again. Grasping for help. Oh man. Okay. Oh wait. Oh, I was supposed to show that. I'm sorry. Or not. I'm sorry, but it's a mistake I made. What you're saying is, I don't have an efficient solution. So what you're saying is, no man, I do not have an efficient solution. Correct. Correct. Excuse me. I don't know, man. This is a tricky question. Alternative way to think, I mean, basically what I'm trying to do is calculate all the possible sums that exist for all the possible subsets. Yeah. I mean, sure. If you could like reuse these numbers, then this would be a lot easier. Yeah, like I said, the problem is that there's a lot of different ways to get to each of these things, and figuring out whether or not you can use a particular number to jump to the next spot, to potentially jump to the next spot, is actually kind of a non-trivial thing, because yeah, listing for a particular sum all the different, if we were to list for each possible sum all the different ways to get there, then we end up actually just listing the sum of every subset, which is not what we want to do. But I mean, my thinking is the part that's supposed to make this efficient is that, like, once you figured out that you can get to a particular spot somehow, then you would not need to I guess for some reason you wouldn't need to recalculate how to get there. I don't know. I don't know, man. This is tricky. This is hard. This is challenging for me. Struggling with this. I don't know, man. I don't know. I don't know. I don't know. Well, I guess what makes this an interesting question is basically every element is either in the subset that you're looking for, or it's not, I suppose. And there are actually, what's interesting is there would be two subsets that you're interested in. So it's either in subset A or subset B, where A and B are going to be equal to each other. So like the first element you could always pick as like one of these two subsets, which is interesting in this case. But then the next element you pick may or may not be in. And actually, you could probably, break these down even further, where you could sort of mix and match elements. Like there might be more than one answer for these subsets as well. I don't know if that helps very much. I don't think so. I don't think it does. I'm trying to think of, like, I don't actually know of a way to do this, like to optimize this. So I'm sad that I already failed the submission. That's unfortunate. Again, I don't want to just use a brute force approach with some like what do they call that? Pruning, like tree pruning, basically. Where you would, pruning, where you would prune different paths and make it more efficient. That probably would work because these are small enough numbers, but I don't know if they're actually small enough. That's the thing. It's like it's relatively small. I don't know, man. I don't have a good answer to this at all. This was a question that came up before too, by the way, because I had answered a question similar to this where they allowed replacement, and I used basically this solution, and or not this solution, but a different solution I was looking at earlier, showing earlier, and it was super efficient and quick and simple, and I felt so good. I was proud of myself. But then I was like, yeah, but if you don't have replacement, then this gets way more complicated. Sure enough, here you go. Here's that question. And I thought about it for a while, and I was like, well, in the worst case, you could do what I keep suggesting, but that's not very good. It's like, it's not very good. It's not very good. Not very good. It actually doesn't help us very much to know that we can get to a particular number for some path, because we would need to continue on that path. Like, there could be a bunch of different paths that come to the same spot, but like, to continue on those different paths, they're kind of disjoint from each other, even though they reach the same number, which is kind of frustrating. How am I going to write a dynamic programming solution if it doesn't matter? If it doesn't matter. Yeah, I mean, actually, that's kind of the point, is that the paths are all unique. All these different sums, they have unique paths. Yeah. Excuse me. Maybe for every sum has its own set of subsets that when summed are you sum up to that particular value. Yeah, and ultimately you're looking for a number that has, well, half the set, the two sums. Basically, you could partition the set into two pieces where the sums of those sets are equal to each other. That's what you're looking for ultimately. Could you figure that out? Wondering if you can add and remove elements from the sets in a way that's efficient, I guess. Really, any subset that sums to half, then all the other elements necessarily would have to sum, would be equal. Right, half the total. Which is great. Excuse me, but then how do you find whether there exists some sum that's equal to this, some subsequence that's summed together is equal to the number you're looking for? Actually, if we sort the list and we have subsequences from left to right, and we say maybe we can use dynamic programming just a different way. So let's say we have an array of values, and I want to say something like at each point we have, so what I'm thinking is, let's sort from left to right all of the indices, and then we want to consider subsequences, like subsequences that sum to a particular value at each index I, we'll say, where like basically the answer at each index I, we want to say these are all the possible numbers that you could get from all the possible subsequent sums, right? And because none of those include, so when you go to the next I, none of those include the I that you're looking at now, the index you're looking at now, right? Oh, so you could just add to all of those. Interesting. Oh, no kidding. Huh. Yeah. You can keep all of them and then add this value to all of those too. and you just set it to true, I think. Oh. Huh. Am I crazy? Wait, is this that easy? Am I just nuts? Did I just miss it before? Am I dumb? Am I, like, what did I, what? Huh. Well then, right, it's like just a much easier question than I realize. Probably. Probably. Excuse me. I don't think you even need to use an index, actually. Actually, you don't even need, like, this is going to be basically like a bit set. Go back to the booleans. Well, this always has at least a number in it, so we don't really care about that. Okay, we're gonna say 4 let's use a pointer. We're gonna say if pointer is true. Right, if that spot is true, then we're going to keep it there. And we're going to say index, or we're going to say auto new pointer. Pointer plus x. New pointer equal to true. Do a couple things. Else possible begin plus x is true. So if that particular spot's not true already, set it to true. And this new value, we have this whole set of things that we could either add the value or not, and not adding the value would leave it true. Adding the value would increase to the next spot. Something like this. I don't know. False, true, wrong. Nice. Also should throw this in here at the end. Faulty reasoning. Perfect. Just what I wanted. With a runtime error. Nice. Perfect. What is going on? Oh. I guess we just have to say. Well, no. No. Oh, okay. That's fine. I guess it would be. I guess it doesn't matter that much. How about that? Still a runtime error, huh? Why? Is that why? I don't get it. What's wrong? Why are there issues? That really doesn't make sense to me because this doesn't. I don't know, man. Yeah, I mean, you literally can't get past the total. It's not possible. Mm-hmm. Alright, why am I getting a runtime error? I don't know. Let's see why. Quite a few checks in there before you get a runtime error, huh? Excuse me. Excuse me. So, why? Oh. Why does this one give me a runtime error? Check one. Really? What? What? Huh? Why? Why though? Oh, okay. 666. Alright, so we get through a bunch of these check 2s, and then all of a sudden we have a problem. Okay. But why though? What could be causing the issue? Is it because of this? I don't think so. I don't think that should matter. Don't think this matters either. Hmm. 1, 2, 4. What's the last? Oh wow. 168,000 more. A lot of check 3s. Okay. It's the last thing we see before check 4. And then runtime error. What is the runtime error? Is it because of this? Check 5. No. What? Why is there runtime error? This doesn't make sense to me. Hello. It's not possible to go. All right, let's do this. All right, let's do it this way. So. If the distance between this and this, if that difference is greater than the distance between, that's why I don't use pointers, man. It's too much effort. Too much confusion. Oh, look at that. Whoa. What? Wait a minute, what? What? Wait, what? How is that? What? Oh, what is happening? I don't know what's going on, man. This is so confusing. This is interesting. This is not supposed to be this complicated. This is supposed to be super simple. Why is this giving me such trouble? So, oh, we're supposed to, oh, that's probably why. Or that has something to do with it, I think. Well, I don't know if that matters. Kind of forgot one piece. So this shouldn't matter though. Actually, it might matter. It might matter actually. I'm thinking about it. Nope. Okay, doesn't matter. Didn't think it would. Oh, actually, that's what I want to do. I want to make it like that. But anyway, this really shouldn't be causing runtime errors. Why is it causing runtime errors? Pause will begin. Where end? Oh, that's why. I see. No. This is wrong. Okay, I think I understand. So, possible is going to be false. Going to be false. No. Okay, wrong. That's what you want to do. And then you want to do this. If, yeah, something like this. Still runtime error. Nice. Great. Okay. All right. So the idea is, let me just walk through the algorithm one more time, describe it. Sort the numbers. First number, you're gonna calculate all the possible sums of subsequences up to and including all the numbers to the left, up to and including all the subsequences up to and including that particular index. And you're gonna do this left to right. So first you have nothing, right? Then you have the first value, have that, set that equal to true, and then you're gonna loop from. Actually, you should do this the other way around. That actually might be part of the problem. You're going to loop over everything that's true, and you're going to add this amount, this value that you're looking at, to all the things that are true, the index, all those things that are true, and you're going to set those to true, right? So the first one, there's nothing that's true, skip that, and then you set that particular spot to true as well. So like if the first value is 1, nothing is true, so you don't do that initial loop, and then you set the spot at index 1 to true. Then let's say you have another 1, you would check everything that's true. You see at index 1 is true, add 1 to that index, now you have 2 is true, and now you have the two different subsequences represented where you have 1 or 1 and 1, right, for the different sums. Or nothing, or 0, right? 0 is always true, but we don't really care about that because we're never going to bother with 0. And then you set 1 to true again, but you already have it, so it doesn't matter, right? The things that you already got, it doesn't make a difference. So we can make this idempotent. Shouldn't matter. Still, we get a runtime error though. Why is this happening? Why are we getting runtime errors? Is this the runtime? Is this the problem? Oh. No. What? Well, nothing happens if we don't have this here. So I guess it's got to be this loop that's the problem somehow. Just a little weird. Okay. So what's happening here that's causing issues? Why is this a problem? Why is this a runtime error? Oh, is that because? That might be why. Yeah, because you could have something that's true. No, but that shouldn't matter, right? Even if we added everything up to the end. See, this doesn't make this should never get beyond the end here. That's interesting. Uh-huh. Yeah. Oh boy, that's really annoying. Okay. You could say int index is possible end minus pointer, and then you say if index plus x is greater than or equal to possible dot size. Bunch of question marks because That's not supposed to happen. That's not supposed to happen. Is that a runtime error? Is that what's going on here? Whoa. Oh, whoa. Okay, hold on. Okay. Alrighty. What is going? Oh, of course. Couple of things here. One, this is supposed to work. Two, what? What? No, man, that doesn't make sense. Oh, you know why? I know why. Of course. Duh. That's why. Because you're supposed to go backwards. Of course. Okay, that makes a lot more sense now. Yeah, duh. If you if you go down the list and you say, oh, I see this 1 is true, set 2 to true, and then you check 2, and now 2 is true, you check 3, 3 is true, you're gonna just run right off the edge. Oh, that is so confusing. This is the index from the back. Actually, I don't think you need to really worry about the rest of this now. Yeah, I guess it would be minus x. Runtime error. Nice. All right. So we're just gonna go ahead and use pointers or use indices. Oh, that is so confusing. And we actually can do total. Yeah, we can just say total. And I is greater than 0. Oops. And then we would say if possible of I, then it actually is possible of I plus. Okay. I think you could still do this if you wanted to. Nice. Still runtime error. Okay. Should be target. By the way. Why is this happening? Is my logic wrong? I really hope not. I really hope it's not the logic that's wrong. Oh. This is just correct now. Okay. What? Excuse me? What is going on? So apparently this happens a lot. Yeah, I mean, of course, right? Like, yeah, that's... Okay. What is going on, man? I don't get it. I don't know. No. How is this, how does this happen? How is this even possible? This is not possible. This is impossible. This is not possible. Please. We take the whole accumulation, the whole sum, right, the whole thing, and we use that as an index. So even if we added everything together, we still wouldn't get this total, right? And somehow we add these numbers, right? So just bear with me here because brain's gonna pop. Brain's gonna pop here. So we go from back to front, all these numbers, we add the first number, set possible of the first number to true. Then we run through this routine from the back. We see one number that's true. We add x to that number, that index, we set that part to true, right? And we keep going up, right? And we keep going, from bottom, from the larger index to the smaller index. And we see a bunch of these, we keep adding. Okay, let's just do this. Right, let's do this. What number does this happen at? Right? How do we do that? How does this even, I don't understand. I think also we're just like randomly getting this one right, by the way. So 36, 37 happens again and again all the way 51, 50. That's not possible. That doesn't make any sense. How does that even work? What? What is this number? Oh, that's why. That's why it's happening. Because that's my mistake. That's why that's happening, of course. Oh man. That's embarrassing. We don't actually need to do it this way. Okay. Gotcha. We actually want to do, I mean, you could do it this way. Yeah, actually, in this case, we are excluding the I is equal to 0, so it actually kind of works here. See the problem. See the problem now. Yeah, the reason was because I decremented the total, cut it in half before. Okay, got it. All right. Oh boy, do I feel silly after that. Yeah, so I think this is a correct algorithm. I don't actually know. I feel kind of dumb for like, a few things, like one, not getting this right the first time, two, getting it, yeah, like taking so long to figure it out, and a lot of other things. Well, we already submitted it before, so let's try again. There we go. Okay. You know, I'm like a little bit embarrassed. Like a little embarrassed here. Like that was not such a hard question. Not a hard question at all. Yeah, it took me a really long time. That took me like 2.5 hours. Really not a hard question. Somehow I just didn't really quite understand. We can actually do better than this too. We don't need to go from the back. We can do. Yeah. Well, we could do it like the following thing. We could do it like this. That's another way of doing this. Oh, actually, can we do it like that? You can say target +1 false. How about that? I'll give you a runtime error. That makes sense. Yeah, it makes sense, actually. I get it now. Well, I actually don't really care. If you say pointer +x, could do it this way. This calculation. Basically, target +1, we want to do the pointer +x. We could do it this way. Yeah, you could do it like that. See, this is still runtime gives runtime errors. Yeah. Oof. Huh. Wait. What? Oh, 100. Give you a runtime error. Why is that? Why did 100 give you a runtime error? Target is 100, 50, 50. Nums is 100. Oh, I think that makes sense. I think I get it. Pointer. Oh, that's actually why. This is why. I didn't think about that. I didn't think about that. Wait, what? Oh. I guess it's just X then. Yeah, okay. Slower. Correct, but slower. That wasn't intended to be slower. That's a lot slower, huh? Does that make that much faster? Not really. So my question is, why isn't this more efficient? We don't actually need to do this accumulation, you know? We can do, yeah, we don't actually need to do that. You can do a constant, which is just nums dot, oops, well. How about that? How about that? Target. Oh, actually, I guess you do need the accumulation then. Never mind. There's gotta be a way to make this faster. There's got to be a way to make this faster. It's so fast here, but it's slow here. What happened? Do we need to sort this? That's another question. Oh, it's still right. Ah, okay. It's faster if we sort it though. It seems to be faster. That's weird. I definitely would not have expected that. It would be faster if you sort it. That's really weird. Huh. Why isn't this faster though? Like this is... Okay, alright. We're gonna try something different. Let's go like the following. Start from the back. Right. Okay. And we're gonna say if pointer's true, then minus x is true. What we're going to say is so much easier to use indices for. Yeah. All right. We're just gonna use indices. It's easier for me to think about. Man. Pointers are faster though. Believe it or not. Believe it or not. Oh. Okay. I need to go to sleep. How do I... Yeah, we're gonna use indices. I really don't want to use indices though. Yeah, we'll just use indices. It's fine. We'll just do it like that for now. Okay. So what I want to say is if I plus x is greater than equal to possible dot size, then we're going to really it's going to be for int j equals j is greater than equal to decrement j pushback false. And then we're going to say possible I plus j equals true. And we're going to do a similar thing over here. I don't think this is going to make things much more efficient, by the way. I think it's actually going to make things slower, after all. If, really for x, j is greater than equal to possible size, j, possible, something like this. Okay. Not nums, by the way. Audible sigh. What is going on? That's probably what it is. No? Okay. Which one's causing issues? Oh boy. Yeah, I thought it'd be that one. Thought it'd be that one. Let's just see if we're at least correct. Yeah, if we don't run into those issues. Nice. Not correct anymore. Alright, good. Glad. Not actually glad, just what we're learning. Alright. Okay. Right, so let's try the one that's not correct. Start with that one. What happened here? False, expected true. Okay. So 1. So we don't enter this loop. J is x, which is 1, greater than or equal to the size, which is 0. Decrement this. Push back 1. J 0. Oh. That's a bit of a problem. Yeah. I see. Right. Really would be the difference. You're looking for something like this. So J is possible size minus x, really x minus the size. So the size is 0, x is 1. Yeah. If the size is 3 and x is 6, you gotta get the size up to 7. 6 minus 3 is 3 plus the extra 1, right? Equal to 0. Yeah. Okay. And how about, no, it's correct now. This should be a little bit different though. This should actually be a similar kind of a thing where J is I plus X minus possible size. J greater than or equal to 0. Should be kind of the same thing. Okay. Alright, how do we do? Oh, it's faster. Yeah. Okay, it's a little bit. This is what I thought. Maybe it would be faster. Really, that's better. Can also terminate early. Throw another if statement in here. Oh, that's a lot faster. There you go. There you go. Heck yeah. Yeah, it's early termination. It's useful. It's efficient. Still not 100%. Like 90%. A little under 90%. What did they do? What did they do to be more faster than this? What could they possibly have done? What could they possibly have done to be faster? I want to say something like this total at the end. This total, something we could do. I guess to make this faster, you could use pointers instead of array accesses here. I don't know. Could try to remove. Oh. Try to remove as many of the array accesses as I can, I guess. Not much faster. Make it all pointer related things. This is fine, I think. You could do. This is kind of challenging. I don't know. Oh, yeah, we could remove the array accesses, but I'm not sure if it really matters that much. Oh, wow. That's a lot slower, huh? Okay, interesting. Wasn't expecting that. No kidding. Let's go back to the array accesses. Really? That's a lot faster. I don't know. I mean, I'm just glad we did the right thing, I suppose. We figured out the right solutions. Just there's got to be a way to do this more efficiently. Maybe we could use a bit set of some kind. I think this gets optimized. Oh no. Really interesting that sorting the numbers has such an effect. Oh. Doesn't seem to matter very much. Whether or not we sort the numbers. If we do it this way. I don't know, man. gonna say we don't really care if we're larger than this target. Don't need to bother with those. Gives you a slight speed up, but not really. Doesn't really help you too much. I don't know how we can make this faster. I think the only way we could really make it faster is if we take this total, do this another way. Oh, maybe we could do it this way. Leave that. Don't get this total. Actually. Don't bother the target of the total. And then say excuse me. Wrong. Nice. The largest possible value you could have. Actually, yeah. Okay, this is kind of interesting. The largest possible value you can have is actually the sum of all the values. So you get the last value. Divide that by 2. And take a look and see what's wrong. Because that's divided by 4, not divided by 2. Still wrong. Why, huh. What do we get here? 1 for all of them? Oh, that's probably why. 100, so you want to take, I see, take this, divide by 2, then take index of that. Now what's interesting is this should actually cause though? Hmm. What does this look like? Hi, hey, it's going Mohammed Garby. Hope your day's going well. Welcome, welcome. How are things? How are you? Welcome, 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 welcome. So, what do we get? We don't actually need to know 0, 1 for that. We just want to know what the size is divided by 2. The third one, right? What's on the third one? Third one is 0, 1, there's 1, 2, 3, 1, 2, 3, 4. Oh yeah, 1, 2, 3, 5. Okay. 1, 2, 3, 5 will give us 11 divided by 2 gives you 5. My output said true. It should be false. Right. Yes. A couple of things there. So int target. Or total. Total modulo 2. And possible total. Something like this. Really? Oh, the second one is... How does that happen? What's going on? Oh, that's why. Keep doing that. That's division by 4 rather than 2. Alright, let's go for it. See what we get. That's a lot slower. Okay. Trying to optimize my code here. Shave off like 4 milliseconds by having this extra bit here. Not really. I'm sad. I'm sad. I messed up this problem pretty badly. I need to go to sleep, but yeah, I done goofed. I done goofed. Actually, you could terminate even earlier. Oh. Ouch. Almost. Almost. Ugh. Ugh. Yeah. Okay. Sure. Oh man. You really don't save that much. Terminating early by putting it here instead of down here. And actually, I don't think you can avoid putting it where you need to put it. Alright, yeah, you don't really gain that much. Man. Fine, and you? Yeah, I'm alright. Thank you for asking. I'm okay. My life's a little crazy. There's a lot going on. It's too much. It's too much going on. Pretty lucky guy though. Very lucky. Extremely lucky. Alright, I guess we'll have to go to the discussion here. But this is a relatively efficient algorithm. This is constant time? Almost constant time? No, it's not quite constant time because of it's proportional. It's pretty efficient, but it's proportional to the number of numbers and also the size of the numbers. I actually think we could possibly do better than this, faster than this. Yeah, we can. Huh. Yeah, we could go actually faster than this. I think. Let me try something. Use an unordered set. Oh, we don't need to do any of this anymore. How about this? Correct? Is it correct? That is not much faster. That's a lot slower. Yeah, unordered sets have that property of like just being a little slow. You know, we can do, but not just that, because we're kind of copying the set each time here, which is kind of a mistake, I think. I mean, yeah, that was 10 times slower, 10 times faster. Um, hmm. I want to see bit sets. Can I make a bit set the size that I want it to be? Tried the problem. It is an easy DP one. Yeah. Yeah, I got destroyed though. I got stuck on it for so long. I don't know if it's an easy DP. Well, actually, yeah, this is easy. This works regardless of, yeah, you're right. Regardless of the size of the numbers. This approach. I don't know if this is quadratic though. I don't think so. Maybe? I think this might be quadratic. This is kind of awkward. Yeah. Let's see. Yeah, bit set as a size. Could maybe try something else. Like we could try. Get rid of these pieces. Go back to what we were doing before. Yeah, another question is, how do I optimize this program so it beats 100%? Solve it with a top-down DP, memory complexity n times sum. Times the sum. Yeah, I have something like that going on. It's pretty good. It sounds like you solved it a lot faster than I did. It took me forever to solve it. Took me forever. I think we don't need this part anymore. Oh, no. We do want this part. We don't need this part. Yeah, we can actually set previous. It's maybe better. I think that was why I didn't want to go through the whole thing. We don't need this anymore. Something like this. Can optimize it using n times sum divided by 2 memory, but I don't think it will speed up the algorithm. Yeah, I mean, I know you can optimize the memory a bit that way, as you described. Actually, yeah. Why am I getting runtime errors here? Oh. Unknown type in, huh? What happened? What happened? Why? I plus x equals true. Plus it equal to target. Set this equal to I plus x. Possible of x. Oh yeah, x could be. Right, that's why. X is. Yeah, x is less than target. That's why. I remember now. Let's go for it and see what happens. Oh. Oh. Hey. There we go. Beautiful. Got that 96%. There it is. That's what I'm looking for. There we go. There we go. That's what I was looking for. Thank you. Now, it's still not 100%, but that's better. That's better. That's what I like to see. That's what I like to see. Tried n times 98%. All right, we're getting closer. N times sum over 2 went from 392 to 212. Okay. Sum over 2. Oh, you're saying, right, optimizing the memory. I mean, that's a lot fast. That is almost twice as fast. It's pretty good. That's big. Hey, there you go. Yeah, almost twice as fast. It's pretty good. Nice. What do you think your time complexity is for your algorithm? I don't actually know what my time complexity is. Oh man. Okay. Well, we shaved off quite a few milliseconds, right? We were at like 44 milliseconds before. Yeah, look at the difference between these. We had wrong 152, wrong 244. Then got down to like 44. Then we had a 500, and now we're down to like 12, which is good, but not as good as it could be, right? Because obviously somebody did better than 12. Somehow someone did better than 12. ON squared. I think it's some weird stuff related to processor cache. Here's his ON squared. I don't think mine's ON squared. I could be wrong. Because mine depends on the sum. Because we loop once through every number, and then within that loop we do a loop through all of the sums that exist. I don't want to say it's quadratic, but I think you're right. I think it's something quadratic. Because this is related to the total number of possible values with regard to the sums, which basically the sum is bounded by, actually the sum could be like unbounded. This could be pretty bad. Given that we have this bound on the values for the sum, it's actually like, yeah, that makes it O(n) squared, because the number of, and basically the number of possible sums is exponential. So by the pigeonhole principle, in asymptotic space, every sum from sort of 1 to basically O(n) squared will be a possibility. Basically, probably you're going to have almost all of those slots filled because of all the possible ways you can combine your different numbers, right? If you have a very large number of numbers and they're bounded by some constant, then that means that at each iteration this is going to do approximately O of k n squared, right? Where the k n squared comes from the summation of all these numbers. And then that means it's quadratic time. Now, this actually could be square root time because of the terminating early and the fact that, or it could be linear, somewhere between like linear and square root, because it terminates early and the sum will have computed the target pretty quickly. I think if I sort, maybe if I sort it'll be even faster, because the sort would imply that the sorting would cause it to terminate even earlier. Yeah, I want to say that the sorting would cause you to terminate earlier because it's that would make it quadratic time, I want to say, because once you've exceeded the sum, like once your sum is basically once your sum is reached or you've gone past it, then you don't have to keep going. Doesn't really have much of an effect. It's kind of interesting. Huh. Makes it a little bit more consistent, it seems. I'm wondering, maybe sorting the vector using 2 pointers will be a lot faster. If there is a solution, the max must be in the subset. If there is a solution, the maximum must be in the subset. I'm not sure what you mean. Not sure what you mean. I don't know how to go faster than this. I was hoping sorting did something for us, but it does make it more consistent. I don't know, it feels like well, maybe not much more consistent. Not really. I don't know, man. How do I get faster than 12 milliseconds? How do I do that? I don't know. I don't know. But I don't know what the runtime complexity is for this either. I want to say there's a way to terminate early, but I don't really know. if throwing this, you know, here would be good. Hmm. Actually, there's probably a way to optimize this even further. So fixing the right pointer and adding the right to the right. If we go greater than the target, we try to subtract the previous number. I'll give it a try. Yeah, I thought faster, but I don't, because the way that because the subsets are not necessarily continuous, if that makes sense. Like, it's not clear what numbers you should add and subtract as you go. Yeah. Because you could have a situation where, like, add and subtract, you can like keep adding small numbers till you're over. And do you subtract a small number, add a big number, subtract some more small numbers, add another big number, subtract, you know, like, it's not clear which way you go, what you add and subtract. This approach, obviously, I didn't really explain it, but the idea is to basically have an array of sequences or sums at a particular index. So each index is going to have this array of sums, and when you go to the next index, you either don't add this number to any of the sequences you've already seen, or you add it, and so that gives you another set of numbers, and you do that at each point, and if you ever hit the target, then you're done. And what happens is there's quite a bit of overlap, right? That's the dynamic programming part. There's quite a bit of overlap, so you don't need to keep, you don't really care how you got to those numbers, because the subsequences that you're looking at, you're not including the next element anyway, so there's no sort of overlap that you could care about. As I said, though, this array grows quadratically. The problem you can run into, though, is you can bound it by the sum, which is what we did, the sum, half the sum. And obviously you don't need to do all that extra processing for like the whole array in the beginning. You only need to do the whole array once you get towards the end. The problem you run into, though, I think, is, yeah, what's the time complexity? It seems to be quadratic. It might even be like cubic. No, it's not really cubic. I don't think it's cubic. Yeah, fortunately these numbers are very small that we're working with, so it works out. But I don't know how to make it faster. Oh man, we're so close, 98%. It's pretty good. I'll take it. Give it a try. Yeah. Let me know. Let me know. Come back to me on that. How it went with the using 2 pointers. I don't know, man. This is as far as I got. 12 milliseconds. Forgot what else I wanted to say. I don't know. I think the discussion would probably have better, more stuff, but the time complexity for me is like kind of not so obvious, not so clear. Yeah, alright, okay. Pretty reasonable, we did alright. I got kind of wrecked by this problem though. I mean, we spent almost 4 hours on this. I actually, um, I got like, I really struggled with this problem. I'm gonna give this one an upvote too. I really struggled with this. Found this to be extremely challenging. I don't think it should have been that challenging, but for whatever reason, I really struggled to kind of think about it, how I could solve it. Yeah, simple DP seems to do the trick. So anyway, let me go. Thank you all for watching. I will talk to you all soon. Have a good rest of your day. Yeah, I forgot. Oh no, well, no, I didn't forget. I just not much else to say. Just appreciate you coming by, and yeah, talk to you soon. Yeah, also Mohammed, I think yeah, feel free to let me know if you were able to find the two-pointer solution or the or just like a faster solution. I'll probably check the discussion maybe. Bye. Yeah. Okay. Okay. Take care. Take care. Have a good night. Talk to you soon.